So you've both got to emplace the waste, stop the water from coming in, reduce the groundwater movement if any groundwater comes in, but simultaneously be able to let the gas escape from that site. So you've got design attributes which point in opposite directions. And that's one of the reasons that tunnel engineering for radioactive waste is a pretty significant challenge.
Did you know that there are 500,000 metric tons of nuclear waste temporarily stored at hundreds of sites worldwide? In the US alone, 1 in 3 people live within 50 miles of a storage site. No country has yet successfully disposed of commercial spent nuclear fuel, but it's not for lack of a solution. So what's the delay? The answers are complex and controversial. In this series, we explore the nuclear waste issue with people representing various pieces of this complicated puzzle. We hope this podcast will give you a clearer picture of nuclear waste, the whole story. We believe that listening is an important element of a successful nuclear waste disposal program. A core company value is to seek and listen to different perspectives. Opinions expressed by the interviewers and their subjects are not necessarily representative of the company. If there's a topic discussed in the podcast that is unfamiliar to you, or you'd like to more closely review what was said, please see the show notes at deepisolation.com/podcasts.
Hello, I'm Carrie Hulak, Deep Isolation Communications Manager. My guest today is Professor Stuart Haszeldine, a geologist and environmental scientist at the University of Edinburgh in Scotland. Professor Haszeldine helped establish a new industry in carbon capture and storage in the UK, Europe, and worldwide, thanks to groundbreaking research on energy and the environment. His current work on the net zero economy includes examining the scaling of carbon capture and storage. When it comes to nuclear waste, he has performed geology, geochemistry, and basin modeling related to site selection and performance safety for the disposal of radioactive and toxic waste in the UK and worldwide. Welcome, Professor Haszeldine. Thank you so much for joining us today.
Glad to be here. That's great.
Okay, well, we'll just get started. I read that the deep biosphere, life underneath Earth's surface, has a volume of between 2 and 2.3 billion cubic kilometers, almost twice the volume of oceans. Your career has focused on exploring this subterranean world for carbon capture and storage and nuclear waste disposal. What inspired you to pursue these studies?
So by background, I'm a geologist, and that's the study of rocks. And I got into geology, of course, as many people do, just by kicking around when I was younger and collecting fossils and minerals. So I developed an interest in the underground. But as you become more and more professionally involved, then you understand that geology is not just about the rocks, it's about the spaces between the rocks in the pore space and how water fills the pore space, or oil fills the pore space, or gas fills the pore space, and about how the underground is actually quite a mobile sort of place. It's not static at all, it's just changing slowly. And so that's how I got interested in that carbon capture and storage, and that's how I got interested in radioactive waste disposal. And the radioactive waste disposal came out of teaching to undergraduate students. So I was teaching an energy course, so obviously them traditionally, conventionally you do, we started off with wood, and then we discovered some coal, and then we discovered oil and gas and nuclear power. So then what happens after we've used the uranium? Where does the smoke goes up the chimney for the other stuff and contaminates the atmosphere. What happens to the radioactive waste? And that led me to start investigating what in the UK was happening to radioactive waste, and that uncovered a whole set of stuff which I personally didn't know. It's perfectly well known, of course, that nuclear power in the UK came out of the militarization of understanding of nuclear fission. But I didn't know that the UK had developed the first commercial nuclear reactor for civil electricity in the world, for example. I didn't know that we reprocessed practically all of the fuel we'd used at that time. And I didn't know about the segmentation of waste into very low level waste, low level, intermediate level, and then high level and spent fuel. So all of that turned out to be a fascinating topic because there's actually a whole bunch of geology involved there, both in the mineralogy and the chemistry of what these wastes are, and particularly in the geologic time which you're being asked to dispose of these wastes safely and securely into what for most people is the impossibly far future. In the UK, we've got 1 million years of the regulations around this. And so thinking about the last 1 million years, there's been an awful lot of changes in the planet with multiple glaciations, different animals and species and hominids arising and becoming extinct, and we just happen to be here now. So we're trying to predict into the far future of that, when our species may or may not exist in the form we recognize it, but we're trying to honor the responsibility to all the other life forms and the water resources of the planet. So that's what got me interested.
Well, I can understand why. It's pretty fascinating. Pretty
it's a big menu, yeah.
Yeah. Well, no, just especially the geologic time piece. We've touched on that before in other interviews, and it just it's hard for most of us to get our brain around what that means. And so yeah, very fascinating. So your research shows there's possibility here to adapt oil and gas borehole technology to create more than 100 million tons per year of CO2 storage to balance hydrocarbon production in the UK. So for those new to carbon capture and sequestration, maybe explain how it works to help with climate change.
Okay, well, the world we're living in is experiencing really quite abnormal rates of warming of the whole world, and it's also experiencing an acidification of the oceans. They've become 30% more acid since industrialization started, and we're also seeing the effects, of course, in changing weather and in melting of ice on the onshore areas. And all of those effects come together as being caused by excess emissions of greenhouse gases into the atmosphere, overwhelmingly by people, of course. And those greenhouse gases are most topically carbon dioxide derived from burning fossil coal, oil and gas, but also nitrogen oxides and also water vapor. But carbon dioxide and methane is the ones we can easily go after. And so carbon capture and storage is trying to say, well, we can carry on using fossil fuels, coal, gas, and oil, and using that fossil carbon. But if we want to use that without damaging impact into the atmosphere, then we have to be able to use those and capture the carbon dioxide rather than just dumping that into the atmosphere as we do now. And it's quite feasible to capture that carbon dioxide. There are numerous methods which have been operating for many decades, since the 1920s in some cases. Carbon dioxide has been transported and put underground since the 1970s, so we know how to do this. And the challenge then is to attach this to industrial scale power plants, large scale industries, using methane for heating or for driving, air conditioning, cooling as an energy source. And how fast and how securely can we do that? So there are many aspects of understanding carbon capture and storage which revolve around the safety and security of storage, predicting into the future. If we put the carbon dioxide underground, the first question most ordinary citizens ask is, when is it going to leak? And what happens? To which my reply is, we know enough about this to say it's not going to leak. And actually, that guarantee we can give you for probably millions of years into the future. So much more than the lifespan of a tree, or much more than a lifespan of a particular industrial facility, or even than a civilization. We can be safe and secure with that. So there are overlapping features of the science and technology investigation between carbon capture and storage and the radioactive waste prediction.
So take us from exploring carbon capture and storage to your work with radioactive waste. So how did you make that transition, and what research are you finding? Maybe draw that link from what you just said there.
Okay, so again, out of teaching undergraduate students in the University of Edinburgh, then we'd conventionally run a field excursion around the Highlands of Scotland, which is a geologically complex mountain belt area, which is quite adequately exposed, meaning you can see the rocks. There's quite a lot of peat around, but that doesn't get in the way. But that was one of the areas where the processes of mountain building were first understood and investigated. But as part of that, one year around, it would be about 1997 or something like that, or maybe even 95, then a program of drilling had been started by the Radioactive Waste Disposal Agency in the UK. I decided to see if we could go and investigate the drill site. And we went there and we looked at the core laid out, so we were given full and free access. But asking the people involved, the technical people involved in all that, was quite interesting and revealing, because it was clear that you had to put an awful lot of different types of geology together to understand the processes and the data and the certainty required to make predictions into the far future. You had to understand where the rocks had come from in terms of their original deposition, how those rocks had been buried, how the minerals in those rocks had changed during burial, and then how they'd been perhaps in the UK slightly uplifted and had cracked and fractured as a consequence, and how then the water moves through those rocks at the present day, takes advantage of any intrinsic permeability and flow through the matrix of the rock, but also water moves very rapidly through fractures in the rock. And we also have to understand how old those different water layers are, because in the shallow part, immediately underneath the ground, there's quite rapid water flow. And the deeper you go, effectively, you're getting older waters, which become more saline, become chemically different, and move much more slowly, even to the extent of effectively becoming static eventually. So all those different parts became quite intriguing. So I started a student funded by a charity, and we then investigated the proposed site for radioactive waste storage in the UK, which was very close to the first nuclear reactor we had in the UK. And we decided to look at the evidence with a completely fresh pair of eyes, because we're not coming from the nuclear industry. We wanted to look at this as geology and as water flow and hydrogeology. So that's how I got into this.
Thank you. And it's definitely been well known. Scientists worldwide since the 50s have considered this to be the best solution for nuclear waste. Yet nothing has been done really to actually make this come to life. Can you kind of speak to that from a scientist's perspective? Why is this the case? We've known about this since the 50s, that deep geologic disposal is a good solution, yet no waste has yet been disposed of.
Well, that's not quite true, I don't think. I'm going to push back on that slightly. Okay. So as I mentioned earlier on, then radioactive waste comes in different grades of not very bothersome to extremely toxic. And so it is absolutely true that the not very bothersome waste has been disposed of in landfill, and the low-level waste is disposed of routinely in special landfill. And those are the big volumes and tonnages of radioactive waste. So that happens in many countries worldwide. But it's also true to say that the intermediate level waste, which is chemically toxic and also radioactively bad for us, is not disposed of. And it's also true to say that the high-level waste, which is effectively almost the radioactivity of the spent fuel, that's not disposed of either, except in a couple of places, such as the waste isolation pilot plant in the United States. And there's temporary storage in Sweden for some of their waste whilst they investigate a full-scale repository. So just to be cautious about being totally correct on that. And so you're quite right that digging a hole and putting the waste in the ground is considered the best available solution. And in some ways it's quite a simple solution, but as we'll see in a while, then there's lots of rules and regulations around that which make that a really complicated thing to achieve in practice. And perhaps the best solution would be to recycle that material, because it's a heat generating material. It has many radionuclides in it. It could be useful, but that's proven to be too difficult, certainly in the UK, because of the mix of elements in there and the difficulty of separating the different elements to have a predictable and reliable behavior. So in some ways, we're taking a slightly unsustainable shortcut by trying to dispose of this waste underground. But we have to dispose of it because it exists and because the waste is basically kept on the land surface at the moment. And that is a really unsustainable, really hazardous place to keep it. So we have to look for places underground. And the reason that's not been achieved is not for the want of trying. There's been plenty of trying right through from United States examples, Canadian examples. Many countries in Europe have evaluated different storage sites for waste, which are all in many ways linked around the common theme of digging a network of tunnels and putting the waste underground. But the big difficulty worldwide has been both convincing the regulators, which is effectively the national police on science and technology. Has the waste proposal proposition been made accurately enough, precisely enough to be certain enough for 1 million years into the future to pass their regulation scrutiny? And secondly, and the biggest problem, is to convince the public about the safety and security of this waste disposal. And of course, particularly the publics who live close to or even on top of a proposed waste disposal site. And that is really a failure of communication, I think, over many decades. And so now it's become more difficult that as soon as you say radioactive waste, then most people in the public will go, no thanks, I don't want that anywhere near me. So we're starting off effectively with a negative perception. And it's obviously much more difficult to overturn a negative perception and turn that not just into a neutrality, but then into a positive acceptance. And so that journey is being undertaken by multiple countries worldwide. And some have had more success than others. As you know, then in Finland, they've been digging a radioactive waste storage site deep underground, several hundred meters underground. And that has proceeded slowly, safely, stepwise. It's taken decades, literally, to gain acceptance of that, and maybe, I think, about another 10 years to excavate this network of tunnels. And that will start operating, we hope, quite soon when I say quite soon, in the next few years. Quite soon is obviously an extended timescale in nuclear waste disposal. And that will be a good example worldwide, be a very visible European example in an area where people live. It's a populated area. And I think examples make a very powerful difference to the perception of the public and also to the perception of political representatives. Effectively, if they can go and visit, you can stand on something. In Britain, we say you can kick the tires of the car and believe that it's going to work. Then you're starting to get somewhere. But it's taken decades to make that progress. But nuclear power hasn't gone away, and it's quite possible that with the mission to produce low carbon energy into the future, then it's quite possible that different types of nuclear power will come back into vogue and be recognized as valuable contributors to reliable electricity generation into the future. So we need to solve the waste problem now and for the future waste as well.
You've examined how radioactive waste can securely be stored for geologic timescales, as you've touched on, is necessary, using tunnel excavation engineering to predict performance of a nuclear waste storage site, which I imagine can help address what you just talked about with the public being concerned about the safety. How does that work? How does the science work? What did you learn through doing that tunnel excavation engineering?
Okay, so we've really reviewed the tunnel excavation engineering. I'm not going to claim to be an expert tunneling engineer,
Okay.
but it's then clearly very. There are several factors, numerous factors involved in doing this. But the basic premise is that if you can safely and securely engineer a tunnel which will stay open for a period of time of many decades, then you can transport the waste in. The waste can be packaged, let's say, safely and securely, first of all. So it's possible to handle that. And in some ways, you can think of this as an analogy to be put on a very smart, safe and secure forklift truck, and barrels and packages of this waste can be taken underground and placed in a horizontal network of tunnels, which are precisely engineered to know exactly where they are, engineered to be lined to keep the flow of groundwater out, and the waste is placed in there and then packed around with a mixture of a clay, the surrounding rock which was excavated, and also some element of cement, and sometimes some iron and copper. And that is known as the near field in radioactive waste jargon. And that is very closely designed to maintain a chemical field to maintain usually a very alkaline pH, a pH of 11 or even more alkaline, and a very low oxidation state, an oxidation state of -50 or -100 even in some cases. Those chemical conditions are designed to keep the waste insoluble, so it doesn't dissolve in any groundwater in the future. And the overpack, if you like, of the clay I talked about is usually considered to be a bentonite, a swelling clay, rather like the vermiculite you sometimes use for roof insulation or house insulation. That clay mineral expands to a very large volume and can absorb lots of ions, chemical ions, onto the surfaces of those minerals as it becomes wet, and also absorb a lot of water. So that's a safety pack, rather like baby nappies around this waste, so that if you have those baby nappies around the waste, if any water gets in, the baby nappies swell and absorb the waste and also attract those metal ions and prevent them from moving around. So that's an engineered containment, which can be very well calculated and very well predicted. But there are also some problems there because the waste can often generate a gas. So we need to engineer to let the gas out. The tunneling excavation itself could generate extra fractures around the tunnels. So of course, the engineers are on a constant mission to reduce that effect. And also the waste itself sometimes contains very short-lived radionuclides, which are still actively producing lots of radioactivity in the immediate term whilst that waste is being emplaced. So you've both got to emplace the waste, stop the water from coming in, reduce the groundwater movement if any groundwater comes in, but simultaneously be able to let the gas escape from that site. So you've got design attributes which point in opposite directions. And that's one of the reasons that tunnel engineering for radioactive waste is a pretty significant challenge.
Now, the US Government Accountability Agency in the US recently sent Congress a memo that asking it to act swiftly to resolve the nuclear waste disposal stalemate that is here, and suggested lawmakers consider deep boreholes as an option to the mined repositories. And how, what is your experience there? And have you thought about using boreholes or other options for nuclear waste?
Okay, so deep boreholes are, I guess, academically, I'd describe that as a really interesting option, and that's supposed to be a neutral term. And it's interesting because boreholes can be drilled at different diameters. So you can, in oil and gas, for example, you might drill a borehole which ends up as being something like 4 or 6 inches across by the time it gets down to 5,000 feet. But it's quite possible in water excavations, water drilling boreholes at shallow depths, you'd drill boreholes which are maybe 50 centimeters across. So when we think of boreholes, we have to think of different diameters that are technically very possible. And then when we're thinking about these tonnages of radioactive waste that you and I are talking about now, we're talking about the high level waste or the intermediate level waste. The total volumes of this waste, even though it's very toxic, the total volumes are not large compared with all the other waste we produce from our industrial culture. And so in the UK, the analogy is made that the total volume of waste is equivalent to about 700 London buses. And so it's quite possible to imagine those parked side by side, and you get some idea of the volume of it. So convert that volume then, if you will, to imagining that as cores of rock, which are maybe 50 centimeters or even 2 feet in diameter. And it becomes possible to think about, yeah, you could drill volumes of rock, numbers of cores like that with boreholes, and convert this volumes of London buses into canisters, which you put down the boreholes. And that seems to be the insight from the deep disposal type of proposal. And that's interesting because we know how to drill boreholes technologically, because the oil and gas industry and the water industry drill these all the time. So we're upscaling and adapting an existing technology rather than inventing a new one. And those can be undertaken quite quickly compared with the decades which it's taken to try and establish a radioactive waste repository without much success at the moment in the United States. And also those can be engineered with a relatively fixed cost, because you know in a uniform rock body, for example, if you decided to drill into a granitic rock body, that's quite a uniform sphere of rock. And that uniformity produces a certainty of prediction. And so then you can have confident predictions into the future about what type of rock you're drilling into. So that's interesting from that type of proposal. But deep drilling and large drilling also produces other types of problems, which the radioactive waste disposal in tunnels maybe doesn't have. And so the types of problems which comes into mind with me is that we know that the radioactive waste is still radioactive when it goes down into the ground or placed into the tunnel. And so it produces heat from that radioactivity. In the tunnel excavations, that heat is handled by spacing out the waste canisters. So the overall heat is distributed, so there's hardly any effect on the rock. So there's a temperature limit of perhaps 100 degrees centigrade maximum. So that's been planned, that's been understood, predicted, we know how to do that. The other type of factor with deep boreholes might be, are you inducing fractures by the drilling process? Because the rock underground is stressed, it's under compression. And as you disturb the rock, it's a well-known effect that the compression of the rock can produce cracks in the rocks surrounding a borehole. Will those, in a deep borehole setting, will those fractures join up with existing fractures or with each other to create a flow system where groundwater can flow? And lastly, you still have the gas problem, which I talked about earlier on. Just because you're putting this waste down a borehole doesn't take away the possibility that gas will be produced by radiolysis of the water, splitting water by radiation, or if you've not made that waste totally sterile, then you could have microbial reactions producing gas by fermentation processes. So there are still important technical problems to overcome. And the biggest problem to me, I think, in my perspective of communicating with the public, is, can you retrieve this if it doesn't go exactly as predicted? Because that's very often a question which the public will ask and regulators will ask. And to me, that's a pretty sensible question, because you can have the trust in the developer, you can have trust in all the calculations of the developer, but you never know what's actually going to happen until you've done it. Again, the first one will be the proof that it can be done properly, and monitoring that and understanding how the rock's behaving will be the most important thing.
Thank you. You were awarded the Scottish Science Prize in 1999, I believe, for your work on radioactive waste. So I'm curious about the project that led to this, and how do you think governments could inspire further work to get nuclear waste innovation moving forward, to get more innovation in the world with this problem?
Sure. Okay. Well, the Scottish Science Prize is is a regional part of the UK, but we have a very, very strong science culture in Scotland, and we have more university students per population, I think, than anywhere else in the world. So it's actually, very much part of our society. So I was very honoured indeed to receive the Scottish Science Prize. And that was for really recognition of the work which I'd undertaken together with a PhD student, Chris McEwen, on understanding and evaluating the proposed storage site from the UK government in the northwest of England in the UK. And so we took a first principles evaluation of that site by looking at the geology, looking at the groundwater, using the information which that radioactive waste disposal investigation had acquired through something like 20 or 30 boreholes. It's still one of the best evaluated subsurface sites in the world. And we really looked at that and said, yes, we understand the proposals from the radioactive waste disposal company, but we don't understand how much uncertainty there is in that. because you can come up with a single value and try and predict geology and try and predict groundwater movement in the future. But we know from the real world in any other geological investigation that there's a range of possibilities, and you haven't got the ability to measure all of that information properly before you start. And even once you've finished, for example, with an oil field, you know a lot more about the oil field. You've produced a lot of oil, but you still don't know everything about that underground. So we really looked at the what would happen if we have the geology arranged like this. There's enough uncertainty, we could say the geology could be slightly differently arranged underground. The faults could be in slightly different places, they connect differently. And in particular, well, let's look at the permeability, the flow ability of that rock and how the fractures connect. So there's a range of fast flow to very, very slow flow, and there are different groundwater layers in the underground. And we put all those together in a range of geochemical models to predict the future, and especially into a range of hydrogeological models where we tried to understand the range of possibilities of groundwater flow at the present day. And unfortunately for the developer at the time, then we could demonstrate that there was a really quite large uncertainty. And some of that could make the site much more safe and secure, much better performance into the future, and that would be good. But unfortunately, some of those possibilities could make the site crash through and fail by a very large margin, the safety criteria. So it's up to a developer to demonstrate the confidence in that, and the developer could not demonstrate enough confidence in that. So I was happy then that this is not acting out of malice at all on our part. It's really saying that if we take a scientific investigation of this, let's look at the most likely, let's look at the good, but we also have to look at the downside. Because if we have got this wrong, then the downside is both very expensive and dangerous, and contamination can arise, and we don't want to go there. And so that's our investigations of that were really the first time that approach had been undertaken in the UK. And that's why we got awarded a science prize.
Seems like a legitimate reason to be awarded a prize.
Yeah, all right. I'll just say, well, we've also carried on, and I've done another more recent evaluation, again with a PhD research student, looking this time at the same region of the UK, but trying to compare sites where we believe that there could be basically a very good geological arrangement for storing waste, where the geology conspires and the groundwater flow conspires to make this inherently a safe and secure place. So we've looked at two sites onshore. One of the existing site we looked at in the 1990s and 2000s. So we've got a baseline expectation of how that performs. Then we've looked at a site which has been identified for many decades as being a very good potential site underneath the landmass of England to the southeast. And innovatively here, this time we looked at 25 kilometers offshore underneath the sea, because in this time span we're talking about of investigation from the 1990s up to where we are now in 2021, then a whole swathe of additional information has become available in the UK from the oil and gas industry in the territory, in the subsea territories around us. So it makes sense to use that information to investigate, is there a safe and secure place offshore? And I knew that geologically, we know that offshore of the place in northwest England, Sellafield, where all this waste is stored, offshore of there, about 20 miles offshore, is a lot of bedded salt layers. So by analogy with the waste isolation pilot plant in New Mexico, bedded salt layers can be extremely secure for radioactive waste disposal, because they guarantee a very, very low probability indeed of any water circulation. So we compared these three sites, onshore in England, the existing traditional site, if you like, and the new innovation of the offshore site. And we've shown there that the offshore site performs much, much better than any of the others. And I'm interested now that about 2 or 3 years after we've published that work, and possibly from their own volition, but the Radioactive Waste Agency in the UK is now explicitly considering further sites further offshore. And so hopefully we've made a positive difference there, and I think a contribution to different thinking.
this is probably an average citizen type of question, but how has the public received the work with the offshore site possibility? I think people think ocean and they think it's going to get into the water. How do you communicate that from a scientific perspective to explain how this works?
So that's a challenge which we're now in the middle of. So I can't tell you how that's going to end, but I can tell you that starting off with our communication, there's a lot of pre-existing trust in communication from universities into the public in this type of endeavor. And particularly universities or researchers like ourselves who've not been sponsored by the radioactive waste disposal industry for decades and decades. So we're manifestly not stakeholders in a particular outcome. And I think that's important to have that trusted messenger status. And so having maybe 10 or 15 years ago come up with some messages to say that particular sites in this region are unsuitable for the following reasons, we're now coming in to actually say, hey, we've done some additional work and these other sites, completely different sites, may be very suitable for a different set of reasons. And that, from the thoughtful people, that gets a good hearing, so they're prepared to take that on board, listen to that carefully. And of course, I'm saying, this is our evidence, this is our information. You make your own minds up about what this is, but there are several positive attributes to this. And the other feature of going offshore is a very obvious one, in that nobody lives there. And so we've found in the past that, of course, the most vehement interest and usually ending up in the most challenging objections come from people who are most directly affected. So in any radioactive waste development, there are some people on land who will live above that site, and they're very, very unnerved by the proposition of radioactive waste disposal because of this long history we've talked about from the 1950s onwards. There's the conflation with nuclear weapons, there's the fear of the invisible radiation, there's the fear of the unknown, which are all understandable. But again, in Scandinavia and Sweden and Finland, it shows that decades of dialogue can overturn that fear. But here in the UK, the people living on top have the most to lose in their perception. Other people living perhaps maybe tens of miles around could gain employment from this. So they're perhaps more in favor of this for 100 years or 200 years worth of employment. But by going offshore, you take away the objections from the people who live directly on the top, and you keep the positivity of the people who maybe have something to gain out of that. But there's still, in the UK, a very complex planning process, and there are different points of view from the people in the surrounding zone. Like in many things, people I think, often like things to stay the same as when they moved into an area. They moved into an area, or they were born and bred and brought up there. They like it just as it is. So big changes are not viewed with great popularity usually, but that's, again, a communication problem, a challenge for the developer to come up with good enough evidence expressed in conventional language, which can be very securely understood and believed. And if that can be done, then the developer has a viable project.
So you've been involved with some activities at the United Nations COP26 climate conference. I would love to hear what role you've played in the event. And we're curious, how is waste from energy technologies being considered in the COP26 discussions, if you know about that?
Okay, so I guess to take those backwards, then waste from energy technologies doesn't have a specific strand that I know of in the COP. It's actually a much higher level of negotiation than that. So, for example, it's taken about 24 COPs to have most people agree that there is a climate problem with carbon dioxide. So this is one of possibly even the first COP where there is no serious objection about the science from different member countries. So in a way that's progress, but it's 24 years of too slow. And another feature which is going on at the moment is what's called Article 6, about how do we trade CO2 liability between different countries? So if we store CO2 in this country here, and can we offset, can we buy certificates of storage from this other country over here? And so those are important discussions, but again, these are multi-year cycles of very, very technical discussion, which moves extremely slowly. So it's not at the level of what do we do about this particular waste stream or that particular waste stream. Though I did go to a nuclear power discussion last night, and the issue of waste is recognized by the several different countries who are trying to undertake waste disposal. It's still a persistent, unsolved, but well-recognized problem, but they have no easy solution to take out of their pocket, if you like. So that's still a journey and a problem which confronts both the United States and many European countries. So what have I been doing in the COP then? It's really been around the issue of carbon dioxide. And so my main research over the past years, since about 2004, has been focused on trying to catch carbon dioxide from industrial emissions and from human activities and put that back underground.
Well, I'd like to close out our conversation today just saying and asking, is there anything we didn't discuss that you'd just like to leave our listeners thinking about? These are so many complex issues that we could talk all day, but just love to see if there's anything else top of mind to close out our conversation with.
So I think by borrowing some information from the way large new innovations often proceed in the energy industry. So deep disposal by boreholes is a really interesting proposition. It could unlock a lot of opportunity for storing radioactive waste, which would then solve or at least provide a route out of a problem which society has had for many decades, because nuclear power could be very valuable in the future, but it's a unique industry where we're really on our third phase of nuclear reactor development without having satisfactorily cleaned up the waste from the first phase yet. So drilling deep boreholes is an important type of approach to evaluate. So my suggestion would be to effectively make a pilot test, is what happens with many other technologies. You have a site which you then develop to be monitored. So you may be going to drill a central borehole, you maybe drill an array of boreholes around that, or install detectors around that where you can install the waste, and then you can monitor the heating effects, the water flow effects, the stress effects in the rock, and gain monitoring and scientific and engineering information from that over a period of maybe 5 or 10 years to try and understand better what the effects are, and that enables you to predict into the future. So those underground laboratories in real time at real full scale are very valuable things. And the United States has the resource and the ability and the size scale to undertake that type of investigation. And that can be then a very powerful way of communicating to regulators and the public that we've built one, and hey, look, we've measured everything about it and it works.
Well, thank you so much. I appreciate you joining us today.
Okay, it's a pleasure.